Okay, hey, what's up? I'm gonna try to explain the Big Bang because I think it's something that a lot of people have heard of, and there's some of what they think is right, some of it's wrong, some of it I don't understand, but I just want to get it clear. There's certain parts I think I understand well, so I want to figure out or explain how scientists know that it even happened. And so first I want to go back, way back. So how we even know anything about the universe. So we start with, we live on Earth, and one of the main things in the universe is where all of our energy comes from is the sun, pretty much, okay? Now, it seems to sort of go up in the morning and then go down and then it's away for a while, but seems to be just in this sort of circular pattern going around us, right? And that takes 24 hours or whatever. But we notice some other patterns. So every 365 days, which we call a year, it seems to cycle between we have hotter times and we have colder times. And in fact, the sun's path seems to be much higher during summer, the hot times, and then much lower during winter. So it makes sort of a lower path instead of a higher path. That's part of the reason it's hotter and colder. But anyway, a good way to explain that is if we realize, well, wait, maybe the Earth is going around the sun, and then, and if the Earth is spinning on a tilt, that actually explains all of that stuff really well. But I won't go into detail. That's just a starting point. Now we start looking at stars, right? We notice there's tiny dots really far, well, we don't know if they're far away. Maybe they're stuck on a sphere, but what we can notice is, so if you're looking at an object with your eyes, you can, if it's close to you, your eyes have to focus inwards. And using that, you don't think about it, but just like let's say I've got this object. If it's here, I can just sort of tell it's close because my eyes have to zoom in. Whereas if I look at something further away, my eyes almost have to be in a straight line. It's sort of called parallax or something. We can do that with the stars. So the Earth, let's say this is the sun, or let's say this is the sun and the Earth is a little dot and it's going around. If we're here and we look at a star, we have to look at a particular angle from here, and then if later on here we look at the same star, we might notice the angles from here and here are slightly converging. They're not quite parallel, but they slightly converge. And using a bit of maths, a bit of trigonometry, we can figure out exactly how far away that star is. For some of them are so far away that it's pretty much parallel, and all we can figure out is it's very far away. It's at least however many light years. Anyway, so using that we can measure, okay, some stars are closer, some are further away. The next thing we want to get into is figuring out sort of what stars are made of. We can use something called spectroscopy, which is a fancy word for breaking down what colors we're seeing. So the way I like to explain it is if you have like a musical chord, say let's say I sing ah, if you had all those three notes at the same time, three people singing, I can't do it, but ah, then you can hear three distinct notes, especially if you're musical. But anyway, even if you've got machines, there are ways to break up the sound into three parts, three notes. Turns out the same thing sort of happens with light, which is another type of wave. If you've got white light, so like the lights here, I don't know exactly what colors they've got, but they could have a mixture of colors. There might be some red, some blue, some green. And if you use a prism, you can see the light split up, like the Pink Floyd album cover. That's a good example of the triangle with white light splitting into all the colors. It's sort of because the colors go at different speeds. I'm not sure exactly why. But we can see what it's made of. And if you look at stars through a spectroscopy thing, whatever, spectroscope, I don't know, you can see exactly how much of each color. And most stars, they don't have an equal amount of each. In fact, there's little bands where they have a lot of that color, or they might have a certain band where there's nothing in that little range. Those are called, like, I think, emission or absorption lines, but that's not important. The point is, for each element, there seems to be, when you sort of burn it, or when there's a reaction, there's these particular lines you get. So there might be a certain frequency of red and a certain frequency of blue for that element. And when we look at stars, we see they have these interesting lines. So for instance, helium, I think, was discovered in the sun originally. I'm not an expert. Anyway, we look at stars that are really far away and we notice it has these lines, and we match it up with elements and we think we can get an idea of what the star's made of. But what was funny was some of the scientists, they noticed these lines, this looks almost exactly like the lines for whatever, sodium or lithium, some element, but it's a tiny bit off. So they originally, I think they thought a lot of them, we must be making mistakes. There's an error, okay? So they kept trying it and they kept getting errors, and then eventually they thought maybe there is an explanation. Another thing you need to know of is the Doppler shift. This is an effect with any wave. So like when a truck drives past and it goes beep, beep, you notice there's a change in note from beep, or racing cars, they go beep. There's a change in note. And if you think about it, it actually makes a lot of sense. Sound waves are these sort of vibrations coming at a certain frequency. If something's coming towards you, those waves sort of get artificially close together. They seem closer, so it seems like a higher frequency. As it's moving away, the waves get more spread out and it takes on a lower frequency. That's why you hear a change in pitch. And it turns out the same thing happens with pretty much any wave. So electromagnetic waves, like light, radio waves, microwaves, but let's just say light in particular. So if we look at a star, if it's moving towards us, the line should be a little bit more blue. And if it's moving away, it should be a little bit more red. And it turns out most stars, okay, and then this is the next step. In maybe the 20s or 30s, scientists, we had like the Hubble telescope, I think, I'm not 100% sure. But we started looking at all these stars and galaxies really far away, and all of them seem to be redshifted. They all seem to be a bit to the red side, meaning that they're moving away from us. And this was very strange. That again, I think most scientists thought this is a mistake. This obviously, they thought the telescope was broken, we need to adjust something. And then they eventually, like anything, when there's something that you don't agree with at first, but it keeps coming up, you have to accept it must be the case. So everything's moving away from us, all the stars and all the galaxies. And not just that, but the further ones away, the ones that are further away, which however we can tell that they're far away, let's not worry about that, they seem to be even more redshifted. So the further ones are moving faster. So it's this expansion. So you pick any two galaxies and they're also moving away from each other. So it's this expanding thing. Now that's what I consider, there's sort of two main pieces of evidence for the Big Bang that I sort of understand. That's one of them. Everything's moving away, and the further things are moving away faster. That's exactly the sort of symptoms of an explosion. In an explosion, every bit, every part is moving away from every other part. Often your scientists or people will have like a balloon and they'll put dots on it, galaxies to represent galaxies, and then when you blow it up, everything moves away from each other. It's a bit like that. So if we backtrack, I guess in theory, I don't know the details, but it seems about 13.7 thousand million years ago, all of these galaxies, all these stars, if you follow it logically, must have been sort of in the same spot. So that suggests that something happened 13.7 thousand million years ago, or whatever, and everything exploded, and that's called the Big Bang. The other main piece of evidence is, obviously, if you have a big explosion, if everything's all tightly packed together, things get hot. In the center of the sun, things are extremely hot. There's other nuclear reactions, but even in the earth, things are hot. Whenever stuff's tight together, it's hot, and there should be some evidence of that. Once there's an explosion, the heat dissipates, it runs out, but it spreads out, but there should be just a bit of evidence there. So something they noticed, if you look in any direction in the sky with a very powerful, accurate sort of detectors, you notice there's this tiny bit of radiation. Like, I think it's like, I don't want to guess, but maybe a few degrees Kelvin, maybe less than that. It's a very tiny amount of energy. It's called the cosmic microwave background radiation, and it seems to be in every direction. There's at least a bit of it, and somehow they did some calculations based on how much matter we can see in the universe, how much energy. If there was a Big Bang, the amount of energy that's left over seems to match up. So it's another very strong piece of evidence. So put it this way, something definitely happened 13.7 thousand or so million years ago, because everything's moving away and there's still this glow that shouldn't, where did it come from? We can't see past it. And I guess in terms of distance calculations, we can figure out it's also the same age. It comes from the same time. The part that I don't like with the Big Bang is that people then decide, oh, it's the start of everything, the start of the universe. That might be true, but I don't know if that seems like a big assumption to me. To me, all we know is something happened, a huge explosion or whatever, that everything that pretty much that we can see came from, but we don't know that's the start of everything. We can't see, and this is where I may just be ignorant, we can't see what's behind the cosmic microwave background radiation. There could be other stuff behind. I may be misunderstanding. It does get confusing, but that's where I think it's good to accept. It's confusing, it's complicated. We don't know exactly what happened at the start. So I think to say that the Big Bang was the start of the universe or the start of everything, the start of time itself, I'm not convinced. I don't understand that, and I wouldn't accept that yet. I'd be skeptical, and I'd encourage people to be skeptical unless you understand something. So I guess the last thing I'll say is, like, in terms of like philosophical implications, I don't think the Big Bang has anything to do with, you know, the purpose of life or why we're here. It doesn't matter. It's just something that happened, and if we didn't discover that, we could discover, I don't know, maybe the universe has been around forever. Doesn't affect what you do day to day. That's ridiculous. So anyway, I hope you learned something from that. I don't want it to go too long, so bye for now.